Today we talk about the higher rank tensors, and then we shall talk about the tensor algebra. Now we shall consider, if we consider n2 functions of the form aij defined by x1, x2, x3, all the way up to xn coordinate system. Now, if due to change in coordinates to another coordinate system with the components x1 bar, x2 bar, x bar, up to x bar n, now these quantities transform according to the equation given here. Then we say that aij forms the components of a contravariant tensor of the second order. So that we have here aij, we have a bar ij transforming to the partial x bar I. You see the I is derived from here. And then we have dxk. Then we have dx bar j. You see j is the component, the contravariant index here by dxm. Then we have we have akm. Then we say that these components aij forms the components of a contravariant tensor. So similarly, if n2 functions of the form aij, now this a with covariant indices transform according to this equation, then we say that aij forms the components of a covariant tensor. You can see now the ij appearing in the denominator here, not in the numerator as in this one. So these two are not the same. So in general, if we have s plus p quantities taking the form a with the s contravariant indices and m covariant indices, the contravariant indices being k1, k2, k3, all the way up to ks, and the covariant indices taking the values m1, m2, m3, all the way up to mp, so that there are p of them. If these quantities transform according to this equation, where you have the contravariant indices k1, k2, let's see here k1, k2, k3, all the way up to ks, and in the denominators here we have the corresponding contravariant indices of this one, t1, t2, t3, all the way up to ts, and then the covariant indices, this one comes down here, m1, m2, all the way up to mp, and the covariant indices of this goes up. Then we say that this quantity a forms the components of a mixed tensor of order s plus p. Notice that s plus p, s is the total number of contravariant indices and p is the total number of covariant indices, so that s plus p is the total number of indices in that tensor. So now we look at the symmetric and skew symmetric tensors. So in general, when we write aij and aji, these two are not equal. They represent different quantities. It's just like in matrices. When we write a matrix A has the components A11, A21, A22. Sorry, this is not 2 and this is 1, 2, A21, A22. Now, when we write this, normally A12 is not the same as A21 in general, because we write, for example, a matrix 3, 5, 7, 9. You can say that we have A12 as 5, A21 as 7. So basically, in general, they are not equal, these quantities. So when we write Aij and Aji, in general, they are not equal. But in some cases, they may be equal, or they may differ only in the sign. So if Aij is equal to Aji, then the tensor is said to be symmetric. If, however, they differ only in sign, so that we have Aij is equal to negative Aji, then we shall say that the two are skew symmetric tensors. The two are skew symmetric. So we can even have a mixed tensor of any order, provided that interchanging the indices j and I will reverse the sign, then the matrix, or rather, the tensor is said to be a skew symmetric tensor. Now we look at the tensor algebra. We shall say that two tensors are of the same type if they have the same number of contravariant and covariant indices. So if we have a tensor A, J, I, and another tensor B, K, L, we shall say that these two are of the same type because they have the same number. Each A has two contravariant indices, B has two contravariant indices. It doesn't matter whether we call them IJ or J or KL. Provided they are both true, each has the same number, then we shall say that these tensors are similar or are of the same type. They are of the same type. So when we write, for example, AI JK and BI JK, we look at the number of contravariant indices. A has one contravariant index, B has one contravariant index. A has two covariant indices, and B also has two covariant indices. So these tensors are of the same type. Now such tensors can be added, or we can get the difference between them to produce a single tensor of the same type. So we can write Aijk plus Bijk is equals to Cijk, or Aijk minus Bijk is equals to Dijk. Now, suppose we consider a tensor of order 2. A tensor of order 2, Ajk. So when we write Ajk, we can always write Ajk plus Ajk, like that. Because you can always break it into 2. Then we add and divide by 2. Of course, we'll get the same result. We can decide to add something else here. We add AKJ. Now this one is different from that. But if we add, we need to subtract. But instead of just adding this, we could write, let me write here. We are saying that when we have AJK, we could write it as a half of AJK plus AJK. Notice that we could also write kj the same way. But what I want us to look at is that this quantity here that we have, let me remove the one below, so that this quantity that we have here, we have written ajk is equals to a half of ajk plus ajk, a half of that. We can decide to add a half of akj, but subtract, so that we are adding 0. Normally when we add 0, this might look something, akj, like that. So whatever we are adding here is 0. This has no effect into the addition. 0 is an identity with respect to addition. So if we open the brackets here now, we could write this is equals to a half ajk plus a half ajk plus a half akj minus a half akj, which we can rearrange. We can group some of this term. We can take the first term and the third term, so that we write a half ajk plus akj. Then we can take the second term and the last term, so we shall have a half ajk minus akj. Now, when we write this component here is a symmetric tensor, or this one is a skew symmetric. It's a skew symmetric tensor, provided that ajk is a tensor. So what we are saying is simply is that any tensor of order 2 can be expressed as a sum of two other tensors, one being symmetric and the other one being skew symmetric. Any tensor of order 2 can be expressed as a sum of two other tensors, one being a symmetric tensor and the other one being a skew symmetric tensor. So we can always do that. We can always do such kind of an operation, and we see that any tensor of the 2 can be expressed with sum of a skew symmetric and a symmetric tensor. Or we can break a tensor of order 2 into two parts, one of them being a skew symmetric and the other part being a symmetric tensor. Let's now look at the multiplication of tensors. And suppose we consider two tensors denoted by B, Ij, KLM, and CQRS, UVWX. Then the outer product, when we talk about the outer product of these two tensors, we'll get another tensor, where we just combine the indices here, the contravariant indices being Ij, QRS. The covariant indices, we have KLM and UVWX. Now, the division is not defined for a tensor of rank greater than 0, because we can only divide constants, or scalars rather. You can divide 1 by 2, you can divide 3 by 4. But a tensor is a generalization of a vector. You cannot divide a vector by another vector. So for any tensor of rank greater than 0, tensor of rank 0 is obviously a scalar, so that one can be divided. But for a tensor of greater than 0, we cannot divide. Then we have the contraction of tensors. And contraction is the process of reducing the number of covariant or contravariant indices of a tensor. It is a process whereby we reduce the number of covariant or the number of contravariant indices. That process is what we call contraction. And suppose we consider a mixed tensor of order 3, order 5 rather. Let's consider a mixed tensor of order 5, so that we have ij as the contravariant indices and KLM as the covariant indices. Now from the equation 1.20 up here, 1.20 here, you see how the a tensor of order S plus P transforms. The contravariant indices K1, K2 up to Ks will appear in the top here. The covariant indices appear in the denominator here, and then these two just appear the other way. So when we come to this tensor A, I, J, K, L, M, how would such a tensor transform? It will transform according to this equation. According to this equation here, you can see now Ij here will appear in the bottom, in the denominator here. KLM will appear in the numerator. And of course, A bar, ST we have S and T here. PQR, this one will appear PQR, so that we have the partial derivative. We are transforming this to A bar ST PQR. So we shall be taking the partial derivative of x bar with respect x bar S, the first index here, with respect to the first index here, dxi, which is the first quantity here. We take the next one, d x bar t by the next index here is j, dxj, and so on. And of course now the others will be coming the other way. The partial derivative, when we come to the covariant index, we shall be having dxk, and then we have the corresponding index here, which is p, dx bar p, and so on. So that we have this kind of equation here. Now we want to replace t with r. We want to replace t with r. I want to write something here. We have a st a bar. What we had the PQR, which transforms to the partial derivative x bar s by dxi, partial derivative x bar t by dxj, then partial derivative xk by dx bar t, the partial derivative xl by dx bar q. Then lastly we have dx m by dx bar r. Then we have a I j k l m, like that. So we want to replace t with r. So we replace t with r here and here. So we get a bar sr p q r. It should be dx bar s by dx l, dx bar r now by dxj, dx bar k, sorry, that's not x bar, it's xk by dx bar p, dxl by dx bar q, then the partial xm by dx bar r, a I j k l m. When we do this transformation, you see now we have this term here and this one. If you work out this two, you multiply out these two, you say that you get dx bar r by dxj times dx bar m, there's no bar there, dxm by dx bar r. This quantity and this one will obviously cancel out, and we have dx bar, we have dxm by dx bar, this is just dxj. Now, when we write the partial derivative of xm, the partial derivative of xm with respect to xj is the same as delta I, delta. This is the same as delta jm, which has the value 1 when j is equals to m, and 0 when j is not equals to m. See that when you are differentiating partially, when you differentiate, for example, dx2 with respect to x1, you get 0. It's only if you write something like the partial derivative of x2 with respect to x1, this one will be 0. But if you write dx2 with respect to x2, this one will be 1. It's like when you differentiate y partially with respect to x. In that case, you are assuming that y is a constant, so the derivative is 0. But when you differentiate y partially with respect to y, then you get 1. So this quantity will have a value 1 when j is equals to m, and 0 for all other values. So that in this case, we shall replace the product of these two with either 1 or 0. 1 when j is equals to m. So when we put 0, then everything becomes 0. But it will become 1 when this j here is equals to m. So we retain only when the quantity is 1, and then replace j with m. So that is what we have here. So we have this quantity here. When we replace r with t, we have replaced r with t here. Then we can put these two together. this and this, these two, so that will give us, when we cancel out dxr here, we get dxm by dxj, which is the same as delta jm, and it's a value 1 when j is equals to m, and 0 for all other values of j. So that when j is m, then we replace this j with m, and we see that now we end up with a tensor where the contravariant index has been reduced by 1 and the covariant index has been reduced by 1. So you see that we had 3 indices here, 3 indices initially. We have S, T. We had 2 indices, contravariant indices, S and T here, and 3 covariant indices, P, Q, R. But now what do we end up with? You see that we have only one covariant index here, which is S. You can see where we have X bar. Then we have 2. This is contravariant. Then the covariant we have P and Q. So when we are determining the order of this tensor here, we say that we don't count the index which is appearing in the numerator and the denominator. An index which is appearing as a covariant and a contravariant is not counted. An index such as m. So we count I, K, L. They are 3. So these are a tensor of rank 3. So in this case, we have obtained a mixed tensor whose covariant index and contravariant indices, covariant and contravariant indices have each been reduced by 1. So in total, we have reduced the order of the tensor by 2. So basically, the process of contraction normally reduces the order of the tensor by 2. So if the tensor was of order R, then we shall get a tensor of order R minus 2. This is the process of contraction. I think I want to stop at that for now. Then in the next one, in the next lesson, we shall look at the inner product of tensors. The inner product of tensors.